Okay. In the previous lecture, which was lecture 5, we synthesized a cam which was rotating anti-clockwise for a radial roller follower. For the same follower motion, we are going to now design a an offset translating follower instead of a radial follower. The base circle and roller radius we set the same. So 35 mm, 5 mm, which means the prime circle is going to be 40 mm. And I'm going to assume that the offset is basically 25 mm, fairly large offset given the base circle is 35 mm. But anyway, you can assume whatever offset. I'm just going to assume that it is an offset, and the offset is basically to the right of the center of the cam. So we are going to offset to the right of the cam center by 25 mm. So how do we proceed? Again, I'm going to kind of rely on Geogebra to go through the construction so that you know how we will do this graphically. So you get a feel of doing this. So let me switch to Geogebra. I have already opened the file. So let me click and make this into a full circle so that okay. So as before, I have located the center of the cam at -4. Now it is showing in centimeters instead of millimeters. So 40 mm, which is -4, and then I am going to draw a prime circle. So this is 40 mm radius. So the x-axis is basically tangent to this, and of course the original case, the follower would have been the radial case would have been going up and down like this, but in this case it is going to go at a distance 25 mm to the right. So what we do is, in order to do the construction, there is something before we draw various things. I'm first going to draw as what is called as an offset circle. So this is drawn with the cam center and the radius equal to the offset E. So this is 25 millimeters. So this is a circle that is drawn with a radius of 25 millimeters, the offset circle. Now remember that the translating axis is out here, so tangent to this offset circle. So it is actually going back and forth here. I'm going to mark the various points for the rise. We are using the same 15-degree increments. So I have B, which is the base. Then I have C, which is 0.42 or 4.2 millimeters. D, which is at 30 degrees, which is 15.7. And finally E, which is the last point on the rise, which is at 20 mm or 2 centimeters. So these points are marked along the vertical line as before. Now what we are going to do is we are going to do the following. So we are going to mark a point F, which is going to be along the horizontal. So AF is basically the reference line from which, so remember that the translating axis is going to be here. So we start from this point. So earlier, you remember, in the radial case we started from the vertical and marked 15-degree increments. Now here in the offset case, I will have this segment AF, which is going to be let me see if I have okay, we'll go through this. So F is basically the horizontal line, forms my reference. And now I'm going to go clockwise from this horizontal position. So in the radial case, I started from the vertical position. Here I'm going to mark angles from the horizontal position, because the angle, the translating axis is going to be tangent, will be a tangent passing through this point F. So we mark a point F prime, which is 15 degrees, F double prime, which is 30 degrees, and of course F triple prime, which is which will take me to 45 degrees. Then I have G, which is the dwell point, so that is away by 22.5. Then G dash, which is in the return part, another 15 degrees, and G double prime another 15 degrees, which is 92.5, and finally G triple prime, which is 112.5. And then of course the last point essentially would take me back to the point which is at the top, right? Okay, so now we join line segments. So we have A to F, which is the horizontal line, right? A to F prime is the second in the rise that we are joining this segment. H is the next line, 30 degrees from AF, and then finally we have 45 degrees. Then of course you have, I'm using a different color just to show that the gray color corresponds to the rise part of the curve, The blue is basically the end of the first well. Then I'm using a different color, which is orange, for the other 15 degrees. And then, of course, you have a total. Uh, so now, remember that this offset circle, the follower axis, the translation axis is basically tangent to this circle. So you can see that. So here is the tangent that is drawn. So I'm just showing you that tangent so that you visualize. So remember that I'm going to, the follower is basically going to move up and down this line. Okay, I'll hide that. And for each of these, I can draw a tangent. And then finally, I'm going to basically look at the various segments, various segments that we have. Let me highlight those. So, okay, where are we? Let me track the. So this is the first segment that we have. So effectively, the this tangent, this is going to sit out here, the first point. Then let me see, where are the other lines? I think let me look at the other lines. Yeah, let me draw. So these are the various tangents. So you see that is one tangent. This is the tangent at that angle. This is another tangent. So this is at 30 degrees. This is another tangent. Sorry, this is at 45 degrees. So we start, this is the first tangent at 0 degrees. So the translation line is here. Then in our inversion, basically it will move by 15 degrees, and the now the new translation axis is basically this. And then when I rotate to 30-degree position, the new translation axis is that. And then finally at 45 degrees, that is my translation axis. The next thing would be this would be the corresponding axis. So I will kind of go through as we pitch the various points. So so this is the 0, 15 degree, the what do you call 30 degrees, and then the 45 degrees. Now we do the same thing that we had marked before. So this now, instead of so what we do is we draw an arc. You can think of drawing an arc from here. I'm not going to show those arcs. So this point B now comes and sits at the point H. This is what we are going to mark. H is basically going to be this point. So effectively I draw an arc. So with the A as center, if I now look at this and draw this, I get over here, this is going to be my H. So similarly, I can locate now. We mark off the various circles. So I can now, I'm not going to show those compass values that I'm looking at. So effectively from H, I'm going to now move. So this is the lowest position that the trace point is going to sit on the prime circle. So from here, the point C will be moved by that distance. So we can mark H on this line, and then we move to get point C, the corresponding intersection. I think that is that. So that is point I. So this corresponds to point C, which is sitting at the distance. So from F prime I will be equal to AC. So that is basically the kind of logic behind this. Then we intersect the next one, so we get the next point on that at 30 degrees, that is point K. And then we again intersect at the 45-degree line, we get point M. Remember, between M and the next one, it is going to be the same distance, so that it kind of comes out like this. All right, then what we do is now we draw the other tangent. So having drawn this, I will hide these tangents, having got these points, just to declutter the diagram. What I'm going to do is effectively to remove the other tangents so that the picture becomes clear. So we will just remove, unhighlight those tangents. So we have got these points already, but I'm going to now construct the other tangents so that the picture is kind of clear for you. Okay. Now we have tangent. This we'll start with this tangent. Then we have a tangent G prime, which is 15 degrees from this dwell position. Then 30 degrees, and then of course the final one, which is basically the last 112.5 degrees. So you have these tangents. We follow the same logic from each of these tangential points. We look at this position, and then we draw accordingly where the how much it moves from this point FH, what is the height by which it moves. So we basically draw from there. So I will so what we do is we draw an arc here to locate H, and then we measure this BC. Then F prime I will be FH plus BC. Similarly, F double prime K will be FH plus BD, and so on. So the same logic we will follow in order to do the um, construction for the return. So GQ, essentially GQ, the distance GQ will be GH FH plus 2 millimeters, 20 millimeters, which is BE. So that is the distance along this tangent. All right. So now let's look at in the same fashion the other points. So we have Q already done. We'll mark S, which is on the return. Then I think it is called O, and the final point, final 2 points U, which is at corresponding to now it is U is the last point, which is on the prime circle. So the distance GU will be the same as FH. All right. So now um, um, how do I get this distance FH? FH is basically, if you look at this as a triangle, AF is the offset E, and of course AB basically. So if you look at this triangle, so AB is basically RP, and this is of course E. So if you look at this triangle, this triangle, we have this is going to be offset. The height of this can be obtained from this RP and E. So root of RP square minus E square is going to be the height of this FH. Okay, so please figure that out from the right angle triangle. So it will be root of RP square minus E square. So that is what will give the height of this FH. All right, so to summarize, we start off by constructing this FH, which is root of RP square minus E square. Then for each of those tangents, F prime I is obtained by adding to FH the lift that I have. So that locates the trace point there. Similarly, this will be at 15.72, which is along this F double prime K. And the last one along F triple prime M, which will be 20 millimeters plus FH. Okay. So effectively, the distance along the tangents will be root of RP square minus E square, which is the base, the starting point, plus the lift, which is y of theta. So you will mark those points along that distance. All right, now we have all these points. Again, I will hide all the tangents. So we have all these points, and we will simply join them by spline functions. Of course, it is not an easy task. I had to do a lot of massaging to get that curve. So of course, you can join by hand if you want to. So the curve looks something like this. Let me complete that curve. Let me see. So I have E2. So various segments that I have, 2, D4, and I think one more segment that needs to be completed, which is over here, and maybe what else is left? M to Q has to be joined. So now with this, of course, I've done a kind of circle arc fit and spline fits to get this final curve. So you can see this is the pitch curve. So H to M is basically my rise part of the curve. M to Q is that first dwell, and then Q, S, O, and U corresponds to the return part, and then of course you have another dwell. Sorry, we kind of shrunk this in size. Let me move this so that you get a okay. So now the next step of course is to draw circles. So we'll draw those circles. I think we are over here, and then where are the circles? Here we start to draw the roller circles. Let me here. So these are the roller circles. So from these points that you have, you start to draw the roller circles. So one over there starting with H. The next one is at I, next at K, next at M, Q. So these points basically are the center. The trace point is the center of the roller. So we draw these circles. We draw, and the final one I think is at U. And then what we do is basically now the idea, as I have said, is to draw a curve which is tangent to these circles. Basically comes up with this. I have already done that. Let me see what I get. I think so this is kind of a crude construction, which is I've tried to keep it as tangent as I can. It didn't come out too well, but that's fine. So, and then the last part is the circular part of it. So you can see I've completed the construction of an offset roller follower. I will summarize this once more, the process in the slides. This is through Geogebra. I have told you how to do this. So let's go back. I'll quickly summarize the same thing. So of course, these things we have done. So what you do is you basically draw an offset circle with the center at the cam center, and then mark off. So first draw the horizontal line. So earlier we were marking everything from the vertical. Now we are drawing from the horizontal line. So this becomes the first thing. The tangent drawn from here represents the line of translation in the actual scenario. F prime is basically, so AF prime is at 15 degrees to AF double prime is at 30 degrees, and so on. So we mark just like before. So we draw those rise lines. Then we draw the first dwell line. Then we mark the three orange lines which correspond to basically the return part of it. And now we draw the tangents which intersect. Of course, H is the first point. I, how did you get that? Of course, we got that from measuring the distances. Remember, FH is basically root of RP square minus E square. That is what FH is. And the it is RP square minus E square is the height FH. And then from there we add to that RP square minus E square y of theta to get I, K, M, etc. Alright, so this is what I mentioned here, that FH is root of 40 square minus 25 square in this case. Also at the tangent point at this thing is D plus y of theta. So this D, I add y of theta, which will give me the various points. Now Q is of course y at 67.5, and the return trace points are along those tangents. We again marked those things and got those points. Joined all of these, and we got the pitch curve, and draw the circles which we did in the GeoGebra, and then draw basically the profile which is tangent to these things. So we now have our cam profile for a roller follower with offset. So now of course what is the big deal about this offset? We will see this, we will pay attention to this as we go along when we do the analytical part. We will investigate the same profile generated analytically, and then look at what is called as the pressure angle, which we had defined earlier. Remember, the pressure angle is the angle between the normal to the pitch curve and the line of translation. So offset does help in reducing the pressure angle, which is important because it generates a side thrust. All right. So to comment on the graphical synthesis that we have done so far, what we did is, remember, we started off by taking the intake valve follower motion, and we have synthesized two cams. In the previous lecture, we did a radial roller follower, and in this we did a offset roller follower. This is a rather tedious way to arrive at the cam profile, but it at least gives you, by going through this, you can see the shape of the cam profile. The key takeaway that I want you to have is that we have used inversion to do the cam profile generation. So we assume that the cam was basically fixed and the follower was basically rotating, because that's the information that we have. So if you look at in all the synthesis procedures, we use the information that we have, and we kind of, whatever we don't know, we say, okay, let us assume that that is not moving, and then use the information that we have. So what information do we have? We have the follower motion information. Therefore we said, okay, I'll freeze the cam since I don't know what is the cam profile. Imagine I'm sitting at the cam, and then we drew the pitch curve for this particular case, and we use that idea to basically arrive at the cam profiles using the pitch curves. Now, of course, we have not done a flat face follower. Knife edge we are not going to do, because that is something that we rarely use because it creates wear and tear on the cam. When we do the analytical equations, which is what the next set of lectures are going to be, we will look at the flat face follower at that point of time. We have not done the graphical. I have limited myself to a radial, a roller follower, both radial and offset follower, and we have left it at that. So from the next lecture, we will move to the analytical methods and then derive the cam profile equations, and then life is very simple. I have the cam profile equations for roller follower, for flat face follower, and then all I have to do is to plug in, put it in an Excel sheet, and then generate the cam profile. Voila, you can plot it in any software that you want, and you have the cam profile. So the proof of the pudding here, of course, we have done a graphical construction. So we'll revisit and see how good our graphical construction, or how close it came to the actual cam profile that we designed when we use the analytical method. Okay, so with this I will stop, and then in the next lecture we will start with the analytical methods.